Hello friends, welcome back to my channel, and in this video I am going to show you how to investigate fatigue behavior of a hip implant geometry. As you know that this is a hip implant geometry into which this lower part is called as stem and this upper part is called as head, and we will apply two materials for this stem. We will use titanium 6Al4V, and for this head we will use alumina, and then we will apply some appropriate forces and will calculate the fatigue behavior, and in fatigue behavior we will calculate the estimated life for the particular forces and the forces at which uh, the this implant geometry will be failed. So for the better understanding, please watch till the end, and we will now start our video. We will go to first into the Ansys workbench, and I will create here a static structural analysis. I will go to engineering data tab. I will create here two materials, which is namely titanium 6Al4V, and I will press enter. I will take here from the physical properties density, and from here isotropic elasticity, and from here I will take tensile tensile yield strength, and for life investigation I will take SN curve. Similarly, I will create another material, alumina. I will press enter. I will take density, isotropic elasticity, SN curve, and tensile yield strength. So the materials I have defined, and I will now give their properties. For alumina, I have already the properties of alumina, and this is showing the properties of various materials which I have already used in one of my paper. For alumina, the density is 3.98 gram per cubic centimeter. For alumina, the density is gram per cubic centimeter, and this will be 3.98 gram per cubic centimeter. I will define isotropic elasticity on the basis of Young modulus and Poisson ratio. What is Young modulus? Young modulus is alumina's Young modulus is 420 gigapascal. So I will go to Young modulus. I will change its unit to megapascal. As there is no gigapascal, I will have to add 3 additional zeros to 420. So it will be 420 and additional 3 zeros. So it is now 420 gigapascal or 4,20,000 megapascal, and the Poisson ratio will be 0.23. Poisson ratio will be 0.23, and the tensile yield strength, what is its tensile yield strength? It is 282 megapascal. Control C, and it is what, 420 megapascal. First I will change its units. This is, and control V, it is 282 megapascal. So the material properties are defined. Okay, and one thing which is left is SN curve. So I will go to tabular is okay. I will change it interpolation to log log. Okay, and we will we will give the properties of alumina. This is the properties of alumina for 10 to the power 4 to 10 to the power 7 cycles. There are alternating stresses and there are cycles to failure. For 10 to the power 4 cycles, alumina will have a alternating stress of 275 megapascal. For 10 to the power 4, which means 10,000, 4 cycles, it will have what, 275 megapascal. 275 megapascal of alternating stress for 10 to the 10 to the power 5, 6 and 7. 10 to the power 5. One more zero here. And the stresses will be what, 240, 205 and 175. 240, 205 and 175. So this is the SN curve. In this vertical side, this is there are alternating stresses, and in the horizontal side there are cycles to failure. So we have defined the properties of alumina fully, and now we will go to titanium, and we will go to titanium, and I will change the units to gram per cubic centimeter, and this to megapascal, and this to megapascal, and this to log log, and this to megapascal. And I will give the density of titanium. Titanium's density is 4.5 grams per cubic centimeter. And what is its Young modulus? Its Young modulus is 110. So I will add 3 additional 0 to 110 here. 110 and 3 additional zeros to creating it to gigapascal. So it is 110 gigapascal, or 1,10,000 megapascal. And what is its Poisson ratio? 0.323. 0.323. And what is its tensile yield strength? Its tensile yield strength is 900 megapascal. 900 megapascal. And going to the SN curve data, I will write here cycles, 10 to the power 4 cycles, 10 to the power 5 cycles, and here because 7 cycles. What are alternating stresses for this? For titanium 6L4V, the stresses are 975 megapascal, 750 750 700, and for this will also be 700. So we have defined the mechanical and fatigue properties of alumina and titanium, and now we will go to the solution. You can also add some other mechanical properties as well of other materials as well, such as here I have added the properties of titanium 6L7Nb, titanium 6L4V ELI, alumina and peak. There are other properties as well. You can refer to my paper, which is namely as mechanical behavior investigation of peak coated titanium alloys for hip orthoplasty using finite element analysis. Okay, so if you have any doubt, you can refer to this paper as well, and you can comment to the comment box as well for discussing any doubt. And now we will go further. Currently I am investigating only for two materials, and now I will go to the analysis. I will go to the analysis and I will go to close this tab, and I will copy the geometry of hip implant here, and I will go to model. I will edit. It is starting, and now it has been started. It is taking some time. It is taking time. So the geometry has been opened, and I will now create the material properties here. I will define material properties here, and I will give the hip stem with the assignment material titanium 6L4V and the sphere head material as alumina material. Okay, so the geometry has been defined, and now I will go to materials. There are materials for viewing the mechanical properties of different materials, and I will minimize the step. I will create another coordinate system. You can see that this is the coordinate system here, and I will have to apply the forces to here. So I will create an additional coordinate system, and I will select the geometry this is sphere and will apply. And now you can see that there is another coordinate system for applying the forces x, y and z. Okay, so now I will go to connections, contacts. Contact region will be, I'm keeping this is bonded because there is no wear and friction analysis. So only for fatigue analysis I don't need to give it fixed frictional analysis, though I can give this to frictional contact as well. And I will suppose I will give here a frictional coefficient of 0.25. So this is the contact, and I will give here a simple mass of, I will create here a method, and I will select the whole geometry, apply, and I will give here a tetrahedral method of meshing, and I will give here element size of 1 meter, 1 mm. Okay, and I will go to structural analysis. I will create here, first of all I will uh, update mesh. It is some like it is taking some time. You can see that the meshing is done, and now I will go to static structural analysis. I will create here a force and a fixed support. I will apply fixed support at the bottom. I will use I will use this face icon, and 1, 2, 2 and 3. So I can apply here 3 faces to fix support, and I will create a force here, and I will reset the geometry, and I will apply the forces at the upper face of this sphere, and I will take here the new coordinate system which I have predefined, and I will create here a load of minus 15700 newtons, and I am randomly taking the forces. You can refer the papers for investigating the better or accurate analysis. I am taking here as a random force of 1500 Newton. So in the solution tab I will just keep equivalent stresses, and for this I will choose the mm, all bodies. Okay, and for this I will take just the head, apply, and for this I will also take this body stem, and I will create here a tool fatigue tool create here fatigue tool. I will define its properties now, and I will go to, first of all, analysis type stress life mean stress theory. I will use here Goodman mean stress fatigue theory. Okay, and time 1, reverse scale factor 1, and time stress life equivalent 1 minus stresses. Okay, one cycle is equal to one cycle. Okay, and now I will insert here life, insert safety factor, and it is okay. All right, and I will give here life to the this body, and safety factor life one body. Okay, safety factor I will change here to 1.1e to 1 10 to the power 7 cycles. I will investigate the life for 1e plus 007 cycle, that is 10 to the power 7 life cycles I will investigate. Okay, and for safety factor, this is life body safety factor. I will investigate safety factor for 1e plus 007 cycles. Safety factor. Okay, and I will also create one more life here, life 2. This is for one body and this is for another body. Okay, and I will create safety factor for this one is for this body and another life 2. Sorry, safety factor 2, delete, yes, insert safety factor 2 for this body, apply for 1e plus 07 life cycles, that is 10 to the power 7 life cycles I will investigate. Okay, so I will recheck this fatigue tool, stress life, Goodman equivalent moment. Okay, life for one body and safety factor for 1 e plus 007 life cycles. Okay, life 2 for this body and safety factor for 1 e plus 007 life cycles. Okay, and I will now solve the solution. So friends, we have now calculated the fatigue analysis and the mechanical investigation of the hip implant geometry, and you can see that the analysis has been done and it has taken around 10 minutes to complete, and now I will show you the solution of this investigation, and I will just setting its behavior. And now you can see that the equivalent stresses for uh, the whole body, all bodies, have maximum of 317.18 megapascal of the stresses, which is far below the and where it is taking the places maximum equivalent stresses, maximum equivalent stresses here, and minimum is where, minimum is in the head. Okay, so the maximum equivalent stresses is taking place at the bottom of the geometry and the minimum is taking place at the head geometry. Okay, and in purely in the head, the minimum stresses is here and maximum is here, and the maximum equivalent stresses for the head geometry is 66.475, for which the uh, for which the stresses are minimum for 10 to the power 7 cycles is 175. So for surviving the 1 e plus 10 to the power 7 cycles or 10 to the power 7 life cycles, for surviving 10 to the power 7 life cycles, we need the maximum stresses to be occurred in the head is below 175. So the head will survive only if the maximum stresses here are less than the 175 megapascal for 10 to the power 7 cycles. So we can conclude that the head is gonna survive 10 to the power 7 life cycles on the basis of this Ascent data curve for alumina, as the stresses are only 66.475 megapascal and the stresses for 10 to the power 7 life cycle should be less than 175. That is all right. So the alumina with the head is going to survive 10 to the power 7 life cycles for sure. Okay, and now the equivalent stresses for the whole body, which means the maximum is here. For stem there is 1317.18 megapascal of the equivalent stresses, 317.18 megapascal of stresses for stem. And from the SN curve we can see for titanium 6Al4V the minimum is 700 megapascal of stresses. If any material produces higher stresses than 700 megapascal, it is not gonna survive the 10 to the power 7 cycles. Here we can see clearly that the maximum stresses are 317.18 megapascal developing in the lower region of this ape implant geometry. So 317 is very well below the this alternating stress for 10 to the power cycle, 10 to the power 7 life cycles. So titanium 6Al4V is also gonna survive 10 to the power 7 life cycles with life of head 1 e to the power 7, 10 to the power life cycle, 10 to the power 7 life cycles is head gonna survive. And what will be the safety factor for head material? It will be 2.6326, which is far better than far higher than 2, which is considered to be a good safety factor. For mechanical designs we take generally 2 safety factor of 1.5 to 2, which is considered as safety factor 1.5 to 2, and this is 2.6, which is far higher than 2, which is considered to be the safest design. Okay, and for the stem there is also the life cycles of 1e7, which is 10 to the power 7 life cycles. The stem gonna also survive, and the safety factor for stem will be 2.2069, which will be considered as safe as per the engineering design aspect. Okay, so we have now seen that how we have calculated the stresses for stem, all bodies, and for particularly the head, and the life for head, safety factor for head, life for stem, and safety factor for stem. So in this way we have calculated and shown that the alumina for head material and titanium for stem material is gonna survive 10 to the power 7 fatigue life cycles. So hope you understood fully the video, you understood the video fully, and if you have any doubt you can just comment me on the comment section and I will try to answer your question as quickly as possible. Thank you for being with me till the end, and thank you so much. Please subscribe my channel and share this video. Thank you so much.